For my Capstone project, I decided to look at math in an application of physics. So I decided what I decided to do for it was make a half-life decay calculator, which normally you don't need to do very much complicated stuff for. But I decided to make it using a Taylor polynomial calculator. So basically what that means is instead of using the E value, it uses a Taylor series to approximate it. So the concept of half-life is pretty simple. Radioactive elements decay over time, and an element's half-life is the amount of time it takes for it to decay to half its original quantity. So if you have, let's say 100 grams of uranium, or whatever element, and its half-life is 5 years, or 100 years, then after 100 years, it will be half its original amount. So you'll have 50 grams of uranium. That basic. And then after another 100 years, you'll have 25. So the equation for half-life is you have the initial quantity multiplied by E to the power of the negative natural log of 2 times T, which is the amount of time that has passed, divided by the half-life of that element. And this can also be written as the initial value divided by E to the natural log of 2 times T divided by H, which is just moving that negative and using exponential rule. So to use a Taylor series for this, what I did was I labeled this natural log of 2 times T over H as X, and then I substituted X in for the Maclaurin series for e to the X, so that I could approximate the e to that value, and then just all I had to do was divide it by the initial amount. Or, yeah, whatever. So the way I set this up was that the code is openly accessible from GitHub, and you can run it on an online shell very easily. So here is the code. We're going to GitHub. For some reason the interface is bugging out. So my program has 3 functions. So if we go down to here, this first one is the basic decay calculator. So what it does is it takes the degree of polynomial that you want, the time that has passed, the half-life, and the initial amount. And it calculates the rate, which is the natural log of 2 times time divided by half, that thing over here. And each iteration, it does the rate to the I to the current degree divided by the factorial of the degree, which is n. So it's the infinite sum of that for however many iterations you decided that you wanted to make. And then after it finds that e to the rate value, it divides the initial value by the rate, or the calculated Taylor polynomial value, and it prints out this total quantity or the amount remaining after that amount of time. The other 2 functions are the derivative and integral. So the way those work is that it's just you take the Taylor series for e to the x, and you integrate or differentiate them to get the rate or area for the half-life equation. I don't know why you'd ever need that, but it's just a demonstration of the mathematics. And so what that ends up looking like is you start off with 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, etc. So if you integrate this, you get x plus x squared over 2 times 1 factorial plus x cubed over 3 times 2 factorial plus x to the 4 over 4 times 3 factorial, and so on. And that's actually, well, if you have x squared over 2 times 1 factorial, that's x squared over 2 factorial. And x cubed over 3 times 2 factorial is x cubed over 3 factorial. So what that ends up doing is that just shifts the entire polynomial over 1. So instead of starting at 1, it starts at here. And now you have the exact same series. And the same thing happens for integration, or differentiation, sorry, where you shift it backwards. So instead of having, so the derivative of x over 1 factorial is 1. The derivative of x squared over 2 factorial is x over 1 factorial, and so on. And so that just looks like 1 plus x over 2x over 2, which is x, plus 3x squared over 3 times 2, which is x squared over 2. And that shifts the entire series back. And so that's the trait of e to the x, which is that it's equal to its derivative. And so in the program, even though I multiply, or I add 1 to the right and then divide it, or for the derivative, I subtract 1 from the right and then multiply it on the outside, for the polynomial differentiation, it will end up being the same amount. And the way you can show this, or test this, if you want, and you can do this as well, because it's extremely accessible, is you just take all this code right here, copy it, and then over here I've linked an online shell which can run a C++ program, and just open that, delete the code, paste that, and run. And there you go. So for our test case, let's just choose a random value, some random values. So we'll say the initial quantity is 100. Might have bugged out. We're going to stop and restart this. Initial quantity is 100. Half-life is 500. Alright, so now let's just do the center. So that means it's just the normal nuclear decay equation for half-life. So it asks you for the time that has passed. We'll post that as 10,000 years. And the iterations. So this is the degree that you want it to be carried out to. So we'll start off with 4. And that's, since we only did 4 iterations, this value is not going to be very accurate. But because it's a program, we can make it as accurate as we want. So now let's just, same time as passed, and let's call the iterations 50, because we can do that. So now we get this value. And we can test to make sure this is accurate by using the formula for half-life over here, and simply just plugging in the values we entered here. So it is the initial amount, so let's go over to a calculator. 100 times e to the negative natural log of 2 times the time, which was 10,000 years, divided by the half-life, which is 500. So that should be, and we got 0.0009536.743. Let's go back over to the shell, and that looks very similar to this if you look at the first two digits. And the further you carry this out, the more accurate it will become. So apparently the program timed out. Let's go run that again. Integer quantity 100, half-life 500. So now what you can do is you can do the derivative and integral. We can just try that for the same thing. So if you want to prove that they are the same, or that those values are similar, you can just do a similar amount of iterations for a derivative, and it will come up with a value that looks a lot like the center value. And that's good, because that means that it's working. And same as for integral. We'll just do that real quick. So integral times 10,000 iterations. Let's do 100, because why not? Right, why not? Let's do 200. 200 iterations. Who knows? Looks pretty similar. It's probably a whole lot more accurate too. And so the only difference between the derivative, integral, and center is that they are shifted. So it might exclude the one or include an extra amount. But since you have so many degrees, it doesn't, the effect that has on the actual value decreases over time. So then so all the commands are up here, and if you ever want to create a new one, or confused, or don't remember the commands, you can just type help to start a new equation, type new, and I guess we have to input stuff now. And then when you're done, you just type quit, and that exits the code, or the program. Thanks.